We have now established the Hamilton-Jacobi formalism and applied it to central force motion in 2 dimensions. Our next step is to repeat this for central force motion in 3 dimensions. And this is fairly typical. The 3-dimensional versions of the equations are apparently much more complex than their 2-dimensional counterparts. But the complexity is all primarily algebraic and in the various manipulations that we have to carry out. It's just a matter of extra bookkeeping. And so we're going to be very careful of our setup and then just follow pretty much the exact same process to get to our final result. We are going to treat our system in spherical coordinates. So we are going to define the components of the position vector of our orbiting body P with respect to the central body at O in an inertial frame E1, E2, E3 that we call I, using the spherical coordinates R for the radius, magnitude of the vector, lambda for the azimuth, that is the angle from E1 to the projection of the orbital radius vector down onto the E1, E2 plane, and finally phi as our polar or zenith angle, that is the angle between the inertial E3 direction and the orbital radius vector. We're using lambda here for our azimuth instead of our usual theta, because theta has already been defined in the system as the argument of latitude, the sum of omega plus nu, and we're going to use it again, and so we pick a new quantity to represent the azimuth. The usual caveat applies here. You will find this exact same derivation in other sources with phi defined as an elevation angle. And so just keep that in mind that frequently you will see exactly the same equations, except all the cosines of phi become sines of phi and vice versa. We write the components of our position vector in the inertial frame as functions of our spherical coordinates, r, lambda, and phi. And then we differentiate this directly to get the components of the orbital velocity vector, also in the inertial frame, also as functions of our spherical coordinates and their time derivatives given by the overdotted versions of the variables. We're going to write the Lagrangian of the system using the specific quantities, so scaled by the mass of the orbiting body. And so the kinetic energy is just the velocity vector dotted with itself over 2, which evaluates to this term here. And then we subtract the central body potential, which is negative mu over r, which gives us this plus mu over r term. And we are allowing for perturbing forces here, but we are going to assume that they can also be expressed as functions of a perturbing potential. And so our perturbing potential, we will call U1, and everything else here, these 2 terms are the L0, the unperturbed Lagrangian, and this is the perturbed part of the Lagrangian. And we will assume that this perturbing potential is a function of the position vector only, and so a function only of our spherical coordinates and not their time derivatives. The canonical momenta for the system are given by the partial derivatives of the Lagrangian with respect to the time derivatives of the various generalized coordinates, which are our spherical coordinates. And so the conjugate momenta associated with the r coordinate is just r dot, p sub phi is r squared phi dot, and p sub lambda is r squared sine squared phi of lambda dot. Next, we write the unperturbed Hamiltonian. So this is the Hamiltonian associated with the unperturbed part of the Lagrangian. And as usual, the Hamiltonian is given by the sum of the conjugate momenta multiplied by the time derivatives of their respective coordinates minus the Lagrangian. And that expression evaluates to this term here minus the original v, which is mu over r. You should all verify that you agree with this expression and note that we have made a few substitutions along the way for these definitions of the conjugate momenta. We see that the unperturbed Hamiltonian is independent of time. And so we know that in this case, the Hamiltonian is going to be constant and equal to the total energy, or in particular, the total specific energy, since that is how we set up this system. We can now proceed to find the generating function for the Hamilton-Jacobi equation, much as we did in the planar case. Remember, our approach is to find Hamilton's principal function, which is the solution to the Hamilton-Jacobi equation, and we do so by defining Hamilton's characteristic function, which is the generating function for these equations. We are going to deviate ever so slightly from our approach in the planar case by setting our first constant transformed conjugate momenta, alpha 1, to be the square root of mu a. You'll recall that in the planar case, we took alpha 1 to just be exactly equal to the specific energy of the system, and therefore equal to the unperturbed Hamiltonian. In this case, the algebra is going to work out a little bit more nicely if we make this definition. But remember, alpha 1 can be any constant so long as we can map it to the unperturbed Hamiltonian. And so it really doesn't matter what we choose. This particular choice is going to lead us to some very familiar looking results, which is why we make this definition. But we can also do the exact same procedure that we're about to carry out with alpha 1 set to the energy, and we would just get slightly modified equations, which would be equally true. So alpha 1 is going to be the square root of mu a, which means that the specific energy can be written as negative the gravitational parameter squared over twice alpha 1 squared. We next observe that the system is cyclic in lambda. That is, the Lagrangian on the previous slide is independent of the azimuth coordinate. And therefore, we can write Hamilton's characteristic function, the generating function for the system, as we know that the conjugate momenta for the lambda coordinate represents a constant of motion. And so we instantly pull out this constant alpha lambda, which is our transformed conjugate momenta. It is multiplied by lambda to get the partial derivatives to work out. And then everything that's left, we call W1. And this is a function of R and phi of the orbital radius magnitude and the zenith angle only. And that means that the original conjugate momenta are partials of only this W1 with respect to their respective generalized coordinates. So let's rewrite our unperturbed Hamiltonian in terms of this new characteristic function. So hopping back to the slide for a second, all that we've done is replace this piece of r squared term and this piece of phi squared term and this piece of lambda squared term with the associated partials of the W1 generating function. And of course, this needs to be squared as well. So we have our unperturbed Hamiltonian is 1/2 the quantity partial W1 with respect to r squared plus 1 over r squared partial of W1 with respect to phi squared plus alpha lambda squared over r squared sine squared phi minus the original potential mu over r. And this is all still equal to the constant specific energy of the system. We're going to multiply all of this by 2r squared, and that gives us, we've also made the substitution for the energy, that is, energy is equal to negative mu squared over 2 alpha 1 squared. And we've also rearranged things so that we've isolated the partial with respect to r on one side and the partial with respect to phi on the other side, along with all of the terms in r and phi. And we have r squared times partial W1 with respect to r squared minus 2 mu r plus mu squared r squared over alpha 1 squared. So that's this term and these two terms is equal to negative the partial of W1 with respect to phi squared minus alpha lambda squared over sine squared phi, which is this term and this term. And we see that we once again have a fully separable system, which means that in reality, our characteristic function, our generating function, is WR, which is a function of R only, plus W phi, which is a function of phi only, plus that original lambda, alpha lambda term. So let's go ahead and perform our separation of variables. We are going to choose negative alpha 2 squared as a separation constant. And so we are going to set this entire term equal to negative alpha 2 squared, and similarly, this entire term equal to negative alpha 2 squared. We start with the left-hand side. So rewriting, we have, that is r squared times the partial of WR with respect to R. And note that we've replaced W1 with WR here because we know that WR is the only piece of W1 that has any R dependence, minus 2 mu R plus mu squared R squared over alpha 1 squared is all equal to our separation constant, negative alpha 2 squared. We solve for this partial derivative and write, that is, the partial of WR with respect to R is the square root of quantity 2 mu over R minus mu squared over alpha 1 squared minus alpha 2 squared over R squared. We next evaluate the right-hand side of our separation equation and write, that is, negative the square of the partial of W phi with respect to phi, again, replacing W1 with W phi, since that is the only piece that has any phi dependence, minus alpha lambda squared over sine squared phi is all equal to our separation constant, negative alpha 2 squared. And similarly, we solve for this partial derivative and write, That is, the partial of w phi with respect to phi is the square root of quantity alpha 2 squared minus alpha lambda squared over sine squared phi. Remember, these two partial derivatives are equal to the original conjugate momenta. The partial derivatives of Hamilton's principal function are the conjugate momenta of the original system. And therefore, this entire expression is the same as P sub r. And this entire expression is exactly the same as P sub phi. We can therefore substitute in the definitions of P sub r and P sub phi in terms of our generalized coordinates and their time derivatives, as given here. And from that, we can write alpha 2 squared is equal to r squared phi dot quantity squared plus r squared sine squared phi lambda dot quantity squared over sine squared phi, which all simplifies to r to the fourth times the quantity phi dot squared plus lambda dot squared sine squared phi. To recap, what we did was solve this expression here for alpha 2 squared and substitute in the definitions of the conjugate momenta p phi and p lambda, which is equivalent to alpha lambda. As a brief aside, let's think about the specific angular momentum of this system. H is equal to r cross v, which means that in our spherical coordinates, it has this form. If we think about the norm squared of the angular momentum, that's h dotted with itself, and this entire ugly matrix simplifies to something that looks incredibly familiar. It is in fact exactly the expression that we just derived. R to the fourth, phi dot squared, plus lambda dot squared sine squared phi. So our separation constant, alpha 2, which is also the second transformed conjugate momenta of the system, is equal to the constant of motion given by the specific angular momentum of the system, and can be written in terms of our first conserved quantity, alpha 1, if we assume a value for the eccentricity of the orbit. Essentially, the process of getting to the Hamilton-Jacobi equations has just given us conservation of angular momentum for free, as it must, because it will identify all conserved quantities of the system. The fact that we chose alpha 1 to have this form is what leads us to regain exactly the same forms of the conserved quantities as we had in our initial treatment of the two-body system. However, again, if we had chosen alpha 1 to be energy or any other constant of the system, we would simply have gotten some algebraic function of h. As a final step here, recall that p sub lambda is r squared sine squared phi lambda dot, and because of the cyclic nature of lambda, this lowercase p sub lambda is the same as alpha lambda is the same as uppercase p sub lambda. If we again look at the angular momentum expression, we notice that r squared lambda dot sine squared phi is exactly the third component of the specific angular momentum in our original inertial frame. And so what that means is that alpha lambda, the third conserved quantity here, is the projection of h onto the E3 direction, which, given our geometry, is alpha 2, the magnitude of h, times the cosine of the inclination of our orbit. Next, recall that for a fully separable generating function w, we can write the transformed generalized coordinates, the capital Q sub i's, as partials of w with respect to the alphas, the conserved conjugate momenta of the transformed system. And the time derivatives of these, the q dot sub i's, will be the partials of our transformed Hamiltonian, k, with respect to those same alphas. In this case, just as in the planar case, we have k equal to h0 equal to the specific energy equal to negative mu squared over alpha 1 squared. And therefore, the time derivative of the first transformed generalized coordinate, q1 dot, is equal to the derivative of this expression with respect to alpha 1, and so therefore mu squared over alpha 1 cubed. And we can integrate this in time to get the generalized coordinate q1, which will be mu squared over alpha 1 cubed times time, plus some constant of integration, which we will call beta 1. If you substitute our definition of alpha 1 into this expression, you will find that this term is exactly equivalent to the mean motion of the orbit, n. And so therefore, what we have just discovered is nt plus beta 1 is equal to the partial of w with respect to alpha 1, as given by this expression here, which we can rewrite as the partial with respect to alpha 1 of the antiderivative of the partial of w with respect to r. But remember, we've shown that w is fully separable, and the only piece of w that has any alpha 1 terms in it is the wr piece. And so this can further be rewritten as, that is, the partial in alpha 1 of the derivative with respect to dr of the quantity 2 mu over r minus mu squared over alpha 1 squared minus alpha 2 squared over r squared, the whole thing square rooted. Note that here we have the partial derivative in alpha 1 of an integral in dr, which means that we are completely free to move this partial inside of the integrand. And so we do so and carry out the partial integration with respect to alpha 1 of this term here, and that allows us to write nt plus beta 1 is equal to the integral over delta r of mu squared times alpha 1 to the negative third times the quantity of 2 mu over r minus mu over alpha 1 squared minus alpha 2 squared over r squared, all to the negative 1/2 power. We next substitute r is equal to a times the quantity 1 minus the eccentricity times the cosine of the eccentric anomaly. Alpha 1 we have defined as the square root of mu a, and alpha 2 we have found is alpha 1 times the square root of 1 minus e squared. Altogether, these things mean that we can rewrite this entire term as the square root of mu over a cubed times the square root of a over mu times 1 minus eccentricity times the cosine of the eccentric anomaly over the eccentricity times the sine of the eccentric anomaly. And canceling all terms, this simplifies to 1 minus the eccentricity times cosine of the eccentric anomaly over the same major axis times the eccentricity times sine of the eccentric anomaly. From this expression for r, we can write that the differential of r, dr, is equal to a e sine of e dE, under the assumption that a and e are constant in our unperturbed orbit. And that means that altogether, what we found is that nt plus the constant beta 1 is equal to the integral of eccentricity times sine of the eccentric anomaly times 1 minus the eccentricity times cosine of the eccentric anomaly divided by this same e sine e term. These cancel, we can directly integrate this, and we find nt plus beta 1 is equal to the eccentric anomaly minus the eccentricity times the sine of the eccentric anomaly. So we set beta 1 equal to negative n times the time of periapse passage, and we have once again rediscovered Kepler's time equation, by my count, for the third time. But this is genuinely cool, because here, just as in the planar central force motion case, Kepler's time equation just falls out of the methodology. We kicked off this whole process just by setting this alpha 1 constant to the square root of mu a, and then everything else follows directly from there, and we retrieve these forms that we previously got through this torturous geometry. Remember, beta 1 is the constant generalized coordinate associated with the transformed constant conjugate momenta, that is alpha 1. So we have q1, or beta 1, the first of our coordinates, and now we can look at all the rest. That is, our second transformed generalized coordinate, q2, which we call beta 2 to remind ourselves that it's a constant, must be equal to the partial of our characteristic function with respect to the second canonical momenta, which itself is a constant of motion, alpha 2. And therefore, we can write this partial as the partial with respect to alpha 2 of the antiderivative of the partial of wr with respect to r in r, because remember, this is the only piece of the characteristic function that has a dependence on r, and the antiderivative of the partial of w phi with respect to phi in phi. These two parts give us all of the pieces of the characteristic function that have any dependence on alpha 2. And so this holds. And once again, we're doing this because we know that we can replace these partial derivatives with the original conjugate momenta in those coordinates. The partial of WR with respect to R is the same as our original P sub R. So we go ahead and make those substitutions, and we write that is Q2 and equivalently beta 2 is equal to the partial with respect to alpha 2 of the integral in R of this entire expression, 2 mu over R minus mu squared over alpha 1 squared minus alpha 2 squared over R squared, the whole thing square rooted, which we previously found was equivalent to our original conjugate momenta in R, P sub R, plus the integral in phi of the square root of alpha 2 squared minus alpha lambda squared over sine squared phi, which again was equivalent to our original conjugate momenta, P sub phi. We can once again take the partial derivative with respect to alpha 2 into the two integrands and evaluate this to find Q2, equivalently beta 2, is equal to the integral in R of negative alpha 2 over R squared times the quantity 2 mu over R minus mu squared over alpha 1 squared minus alpha 2 squared over R squared, all square rooted, plus the integral in phi of alpha 2 sine phi over the square root of alpha 2 squared sine squared phi minus alpha lambda squared. And as one more final step, remember that we have also discovered that alpha lambda is the same as alpha 2 cosine of the inclination. And so alpha lambda squared is the same as alpha 2 squared times cosine squared I. Here, we're going to need to appeal to a result from spherical trigonometry. And that is that in this system, the angle phi, the zenith angle phi, is given by the arc cosine of the sine of the inclination times the sine of the argument of latitude. Remember, argument of latitude is the angle between the line of nodes, which is in the E1, E2 plane, up to our radius vector. Phi is pointing down from the direction orthogonal to this plane down to the radius vector, and the inclination is the angle between the plane in which the radius vector resides and the E1, E2 plane. If you put all of that together, then you find that phi is the arc cosine of sine I sine theta. The derivative of phi, d phi, can then be evaluated as sine I cosine theta d theta over the square root of 1 minus sine squared I sine squared theta, again under the assumption that theta is the only thing that is changing here, because for a pure unperturbed two-body orbit, I is constant, and only theta has a time-varying component via the new piece. We substitute these expressions into the second integral of our equation here, also canceling out the alpha 2 term as we go along, which appears everywhere in the numerator and denominator. And we find that this entire thing becomes, that is the integral of sine I cosine theta d theta over the square root of 1 minus sine squared I sine squared theta itself over 1 minus sine squared I sine squared theta times sine I cosine theta. And holy cow, everything cancels. Everything in here goes away. This entire integral is just the integral of d theta. And that means that this entire thing just works out to theta plus some constant of integration. For the first term, we are going to substitute once again. Alpha 1 is equal to root mu a, alpha 2 is equal to root mu a times 1 minus e squared. For r, we are now going to use the form as a function of the true anomaly. So r is a times 1 minus e squared over 1 plus e cosine nu, which means that dr is now ae 1 minus e squared sine nu over 1 plus e cosine nu quantity squared d nu. We substitute all of this into here, and we get, that is, this entire integral in dr becomes negative the integral of e times root a mu 1 minus e squared times sine nu d nu over a times the square root of e squared mu sine squared nu over a times 1 minus e squared, all times e squared minus 1. And once again, everything cancels out. All of this goes to 1, And all we're left with is negative the integral of d nu, which is equivalent to nu, negative nu, plus a constant. We got to these integrals by trying to evaluate the second transformed generalized coordinate, the second constant of motion in the system. And what we've just discovered is that beta 2 is equal to theta minus nu plus some constant. We can take this constant to be pretty much whatever we want. So let's just go ahead and take it to be 0, because we can do that by matching up initial conditions. Beta 2 is just theta minus nu, which is exactly omega. We have suddenly discovered one of our fundamental Euler angles describing the orientation of our orbit that just falls out of the Hamilton-Jacobi analysis. Again, the only thing we had to do to get here was set this alpha 1. Everything else is just mechanical clockwork. The process automatically retrieves for you the fundamental conserved quantities of your system. We have one more, and let's see how that works out. Our last coordinate is beta lambda, which is equal to the partial of the generating function with respect to the canonical momenta alpha lambda, which is the same as the partial with respect to alpha lambda of the antiderivative of the partial of omega phi with respect to phi, d phi, plus alpha lambda lambda, because remember, we started this entire process by noting that our system was cyclic in lambda, and so we had our initial trivial separation as w of r and phi plus alpha lambda lambda. We do the same thing that we've now done twice before. We substitute for this term the original conjugate momenta of phi, which you will recall had the form. And I will stop and note here that we needed to include w phi, but not w sub r, because w phi actually has an alpha lambda term in it, whereas wr is independent of alpha lambda. We bring the partial derivative inside of the integrand and also take the partial of this last term, and we find beta lambda is equal to negative the integral of alpha lambda over sine phi times alpha 2 squared sine squared phi minus alpha lambda squared, the whole thing square rooted in phi, plus a single term of lambda. We know that alpha lambda is equal to alpha 2 cosine of I. We've already figured out how to express phi in terms of the other angles of our system, which means that we also have an equivalent expression for d phi. And so we find that this integrand is exactly equivalent to negative alpha 2 times cosine I, sine I, cosine theta, d theta, over the square root of 1 minus sine squared I, sine squared theta, times the square root of alpha 2 squared times 1 minus sine squared I, sine squared theta, minus alpha 2 squared cosine squared I. And this is all rather eye-watering, but it clears up very fast, and all that's left is cosine of I over 1 minus sine squared I, sine squared theta, d theta. If you squint at this expression long enough, you should be able to convince yourself that this is equivalent to the derivative in theta of the arctangent of cosine I times the tangent of theta. And of course, it's not strictly necessary to do this in the forward direction. You can just evaluate this derivative and prove to yourself that it gets you back to this expression under the assumption that I is constant. Remember, we are taking the integral of this expression with respect to now theta. So what we've actually written down is beta sub lambda is the arctangent of cosine I tan theta plus lambda. At this point, you were probably expecting something that maps directly back to our original system, but it doesn't quite look like we've gotten there. But here, we have to use another result from spherical trigonometry to help us along. And that is that this arc, the arc between the line of nodes and the projection of our orbital radius vector onto the E1, E2 plane, is in fact the arctangent of cosine I tan theta. If we add this arc to lambda, which is the angle from our inertial E1 direction to the same projected line, what is left is omega. So in fact, we have recovered yet another one of our constants of our original orbit in the form of the third Euler angle. We have now discovered the full set of canonical orbital elements. Beta 1 is nt naught, where t naught is equivalent to t sub p, the time of periapsis passage, or the initial time of our system. Beta 2 is equal to the argument of periapsis of the unperturbed orbit, and beta lambda is equal to capital omega, the longitude of the ascending node of our unperturbed orbit. The canonical orbital elements are known as Delaunay elements, or Delaunay variables. These are examples of what are known as action angle coordinates, where the action are the momenta and the angles are the generalized coordinates associated with the momenta. But remember, because we got these via construction of the Hamilton-Jacobi equation, all of these are guaranteed to be constant. And they are. And they map directly to our original Keplerian orbital elements. In Delaunay's original work deriving these, the letters capital L, G, and H were used to describe the action, and lowercase l, g, h were used to describe the angle coordinates. And you may still find this nomenclature in some texts, but typically this is avoided because L and H and G are used in lots and lots of other contexts and have already been defined by us as things like the semiparameter and the specific angular momentum and gravity. And so we will typically use either this set or their Keplerian mappings. Just as in the planar case, remember that the main utility here is not recovering these constants, but rather the equations associated with them and how they can be used to now treat perturbations. The whole point of this was not to focus on H naught, but really to give us a handle on what the perturbing Hamiltonian, H1, associated with that perturbing potential U1 is doing. Everything we've said so far about the dynamics of H naught is just a recovery of Kepler's laws. But now we can add in this H1, and that means that alpha dot I is equal to the partial of just the perturbing potential with respect to the generalized coordinate beta I. And the time derivative of the generalized coordinate beta sub I is equal to negative the partial of the perturbing potential with respect to alpha sub I plus the partial in alpha I of mu squared over 2 alpha 1 squared. We now have an exact set of differential equations as functions of any perturbing force that can be written as a perturbing potential. As we've already stated, we can average the rates of change of these parameters and we can find their average effects, or we can directly average the perturbing potential over the course of an orbit and then calculate the rates of change of the relevant orbital elements. Delaunay's elements and variables are very useful because they are canonical, but they are somewhat abstracted from our geometric understanding of orbits. It would be nice if we can do this for Keplerian elements, which are not canonical, and it turns out that we can get differential equations of this form. But before we do that, we have to explore another property of the Hamiltonians, and that is their symplectic nature.